To illustrate application of double integral in physics, let me compute the moment of inertia of some simple bodies. So what does it mean, moment of inertia? If we start with kinetic energy, which is 1/2 times the mass times square of the velocity, then if we have a rotating body, rotating with some velocity omega, angular velocity, then the velocity of each point depends not just on the rotation itself, but also on the distance from the axis of rotation. And this is r times omega, where r is the distance from the axis of rotation. Then the kinetic energy of one single point is 1/2 of mass, and v squared is now r squared omega squared. If we have more than one point, we can consider point number 1, point number 2, point number 3, in general point number I, and we have m sub I, the mass of I point. Omega is a constant for all the points in this solid, but r depends on the point, how far it is from the axis of rotation. And then we sum over I running from 1 to capital N, but N is the number of points. This can be written in the form 1/2 sum of r I square n I times omega square. And if we close this expression into bracket, then again the kinetic energy is a product of three expressions. 1/2, that's the same, times something that depends on the body itself, independent of the motion, and something that depends on the motion alone, independent of the body, similar as here. And this quantity is denoted by J, and it is called moment of inertia. Not to be confused with the Jacobi matrix of first partial derivatives. The same letter for two different meanings, not to be confused. So this is in the case of isolated points, when the mass is distributed in these discrete positions. And in general, if we have a mass distributed in somebody like your human body, the sum comes to integral. So we can consider J to be the integral, and in general, if we are in a three-dimensional space, this will be a triple integral over the whole body of r squared, and m can be written as a product of the density rho times the element of the volume. Possibly the element of the volume can be written dx times dy times dz. So this is the definition of the moment of inertia. Well, and the density r may be either constant for a homogeneous body, or it may be a function of x, y, and z, as is the case for non-homogeneous objects. Okay, let's compute the moment of inertia of some simple objects. Consider a rod that rotates around a circle, and we want to compute the moment of inertia. and consider the homogeneous rod. So the moment of inertia, if we visualize the rod in this way, an object which is long and very thin, with length capital L and area of the cross-section capital S. Then we can start with the origin in the middle, and we can have some coordinate x. So that will be the integral from minus L half to L half of r squared. This is the square of the distance from the origin, from the axis of rotation, but if the axis of rotation goes through the center, then r is x, so we have x squared, times the mass of each little piece, which is the density, times the volume. And volume is the surface of the cross-section times dx. And that's all. In a more general case, if the rod is not homogeneous, then the density rho may be a function of the position x. In a still more general case, the rod may have cross-section that varies with position. It may be thinner in some parts and a little thicker in different parts. So even S may be a function of x. But we will consider rho and S constant, so we can factor rho and S in front of the integral. And this is an even function integrated over symmetrical interval, so we can take 2 times from 0 to L half x squared dx. But the antiderivative is x cubed third, so we have 2/3 rho s, and cube of s L half is L cubed divided by A. So 2 divided by 8 is 1/4, so this is 1/12. And if we write L squared times L, then L times S is the volume V times the density rho is the mass M. And this is the formula for the moment of inertia of a homogeneous rod. In the next section, we will compute the moment of inertia of a homogeneous disk and then of a homogeneous ball.